welcome everybody. So today we're going to talk about the wave nature of matter. We're going to move away from Bohr's model. So the issue with Bohr's model was that he was really a one electron type of guy. The problem with his model, when you tried to look at it mathematically, you could see that it explained what was going on in hydrogen really well. But when you try to mathematically apply his model to other elements, the math started to fall apart. At the same time, scientists were realizing that matter, especially small particles of matter, things that had very tiny masses and moved at very fast speeds, were or could act as waves. And this is where the whole idea of the de Broglie wavelength comes into play. And so the de Broglie wave nature of matter basically says that particles, very small particles, are vibrating with a certain frequency. And that vibration can be manipulated in such a way where you can actually produce images with it. You can also then apply the idea of the wave nature of matter to the atom and think of electrons as if they exist as these standing vibrating waves. These standing vibrating waves tell you where the electron can exist in an atom. It is akin to constructive and destructive interference that you would see if you were looking at a sound wave, or if you were looking at light patterns, going through what the famous double slit experiment was, where you have light shining through two small openings, and that light that passes through then creates an interference pattern on the next thing that it hits. And so we see that electrons, if you do the same double slit experiment with them, will form the same type of pattern. So let me show you, what the de Broglie wavelength equation is. And this one you saw last year. And so basically what we do with this is we set the E equals mc squared equation from Einstein equal to Planck's constant for energy. And if we set them equal to each other, then and solve for wavelength, then we get wavelength is equal to h over the mass. And I'm going to replace c, which is the speed of light, because nothing can travel at the speed of light, with a velocity. And so this is the de Broglie equation for the wave nature of matter. What it says is that matter with a certain mass and velocity will have a certain wavelength associated with it. We can apply this to the atom for electrons. This gives us an idea of where the electron is located in the atom. Now, a couple of important things here. The mass has to be in kilograms, and velocity has to be in meters per second. So the mass has to be in kilograms, and the velocity has to be in meters per second. So now we won't see this if you're like a macroscopic object. It's like, somebody running down the street doesn't have a wavelength that's visible. But again, with electrons that are really small and moving really fast, we can actually determine what their wavelength is, and we can use that. And here are some, images that electrons can produce. These images on the right here are from an electron micrograph. And what they do for this is they take a beam of electrons coming from a certain source and they focus it using magnets because they're charged. They then aim it at a target that's embedded with gold particles, and then they're able to, based on how the electron waves are diffracted, get an image. And because the wavelength of the electrons are so small, they can actually resolve up to very small objects. On the left here, this shows you the typical double slit experiment where there's a wave front coming through. It is obstructed except for where there's two openings, and then the waves pass through there, and now the two wave fronts will come together and form a diffraction pattern. Now what that actually looks like? Well, it looks like something that we have here on the left. And what's interesting is these letters, they're unmarked. But when you look at, for example, D and E down here, D is what happens with electrons, E is what happens with X-rays. I think that's kind of cool. X-rays, which is, pure energy, it's not matter, those have a certain diffraction pattern. They use that to resolve structures of proteins and other molecules. But electrons give off the same pattern. So how do we apply this to the atom? Because that's really what we're here to do. And so if we if we, consider the wave nature of the electron, we can think of that constructive and destructive interference that we see when we do a double slit experiment. And we can apply that to the atom. And the idea is that when the electron's wavelength is in a constructive interference pattern, you will get an area that is able to support the location of an electron. If you have a situation where there's constructive interference, like over here that I circled and pointed to, well, then you'll have a situation where the electron can't exist. This will be called what is known as a node. In class, I'll show you some, standing waves where you have areas where the waves exist, areas where the wave is impossible to exist, or where it's impossible for the wave to exist. And what you're going to see is that the electrons, they have the same properties. They're able to exist only where their wavelengths will overlap in a constructive interference pattern. So they call this what's known as the wave function. So the wave function, it's a mathematical equation. This is all about probability. And it tells you where you're going to find the electrons in an atom based on the wavelength of the electrons and the constructive interference pattern. Sometimes we'll refer to things as electron density, and this is what's known as an orbital. It's the square of that wave function. And what it allows you to do is it allows you to, basically locate the approximate area of where you're going to find an electron. The problem with this, though, is that you really can't tell exactly where the electron is. The electron's moving around constantly. The electron has a wave property to it, so you always have some uncertainty to it. And this is known as the Heisenberg uncertainty principle. We're not really going to go into the math with this, but it's important that you know that it exists. When we think about, where is the electron, what is its electron density, we can tell pretty much with about 90% certainty where we're going to find the electron. We don't know with 100% certainty where the electron is. So the term that we're going to use to describe this, electron density, or the square of the wave function, the probability, is an orbital. So the orbital, it's going to correspond to a specific wave function, a specific solution to this math equation, which I'll show you in a second. And it's going to describe where that electron is most likely going to be. Now, you know about orbitals from last year, but we're going to go back through what the, quantum numbers are. It turns out for these orbitals, these wave functions, there are 4 variables that are used to describe where the electron is to be found. The first one is called the principal quantum number n. It's equivalent to what's known as the energy level. You can see here that n is going to have a whole number value, 1, 2, 3, and so on. Now within these energy levels, these principal energy levels, there is sublevels. And those sublevels, they're described by the second quantum number, also known as the azimuthal number, and it's given the script letter L. Because the sublevel is within the energy level, it is determined by the energy level. Its value is n minus 1 down to 0. I'll show you on the next slide what the chart looks like. Now this, again, this is the sublevel. So it's the sublevel of where the electron is. We know this as S, P, D, and F. But these actually have numerical values, and they're based on what energy level they're in. The next quantum number is the magnetic quantum number. And what this describes is the number of orbitals. It's telling you where the orbitals are in space. So the XYZ coordinates. The more orbitals that you have, the more possibilities that there'll be in an XYZ, different XYZ coordinates. So for example, if you just have one orbital, you're only going to have one possibility of having in space. It's going to be a sphere. Whereas if you have multiple orbitals, well, in that case, then you could have one in the X axis, one in the Y axis, and so on. Now let's take a look at these quantum numbers here and see how they work out. So remember, n is the energy level. And in energy level 1, we can have a sublevel based on n. Sublevel based on n. Remember, the sublevel is n minus 1. So if we do 1 minus 1, we'll have 0. That's always given the designation S. This is why energy level 1 only has, one S. It doesn't have one P, because there's no sublevels that are supported on that energy level. Within that L equals 0, we can find the ML, which is plus or minus L. So what's plus or minus 0? 0. And that means that we have one orbital, which we draw with a box. In that orbital, we can put 2 electrons, and each one has an opposite spin, plus 1/2, minus 1/2. And so that opposite spin will look like this, up 1/2, down 1/2. If we go to energy level 2, well now, energy level 2, the sublevels are, let's actually change the color here. Energy level 2, the sublevels are n-1, so 1, and 1 - 1, 0. So in energy level 2, we have 2 sublevels. One is given the designation P, and the other one is S. Now within each one of those sublevels, we have orbitals. For sublevel S, we have one orbital. But for sublevel P, since it's plus or minus 1, we have -1, 0, and 1, 3 orbitals. And in each of those orbitals, we can fit 2 electrons for a total of 6 electrons. If I go to energy level 3, I have 3, and then I have n-1 down here for L, and that's going to give me, oops, sorry. So for energy level 3, I'm going to have n-1, so 2, n-1 again, 1, n-1 again, 0. And so now those are S, P, and D. And now we can do the orbitals again. This will have 1 orbital, this will have 3, this will have 5. Each orbital can fit 2 electrons, 2, 6, and 10. What I'd like you to do is energy level 4. And so when we come in tomorrow and talk about this, we can go through all of the values for energy level 4. Now, what does this look like in terms of, an equation? Well, this is the math behind it. This is Schrodinger's equation. Notice he has values here. He has values for N, L, and M. And that's for each one of these orbitals. This one right here is 1s. This one right here is 2s. These orbitals here are 2p. And they do this through 3. Or at least through, they do this through 3. So each one of these orbitals that is within an energy level, a sublevel, and then an orbital, each one has a specific equation. That equation is the wave function. That wave function tells you the probability of finding an electron. You don't need to know these equations. I'm not going to test you on them. They're there because a lot of people ask me, hey, what does this mean? Is there an equation? And yes, there is. So what we'll do next time is we'll do electron configurations, but I really need you to make sure that you know these values and these quantum numbers. All right, thanks so much.